Hello ladies and gentlemen, and here we are taking a look at solving problems using similar triangles. So this corresponds to chapter 1.4 in your textbook, and we're going to notice that when we solve problems using similar triangles, that similar triangles can be used to find heights or distances that are difficult to measure, and similar triangles have many practical applications. And we're going to take a look at some of those practical applications today. So what we have here is we have an example. We have a stick. A stick's going to be about 3 meters tall. That's a pretty big stick. I think I'd call that a pole. But that's a 3 meters tall stick, and it's going to cast a shadow of 4 meters long. A nearby tree casts a shadow of 15 meters, and the question is, what's the height of the tree? Okay, so this is what's going on here. And these questions require you to read the question and think a little bit before you do much. So we've got a tree, we've got a sun, and we've got some shadow. And what happens is the sun's rays come down and they hit the tree and they get bounced off the tree. And so the sun's lights can't get over to this side of the tree, and that's what a shadow is. A shadow is actually the absence of light. Okay, so this shadow is going to run along the bottom of the ground, but the thing is, it's only going to be as long as there's going to be a ray of sunlight that's able to get over top of that tree and make it down to the ground. And when it does, then it's going to have light all the way along here. So this shadow is only going to be from all the rays of light that come down and get blocked by the tree. And that's going to create the shadow. Now, what we want to do is find out the height of this tree. We're going to want to find out x, so the height of this tree here. And this is the shadow, which is obviously along the ground, and that's going to be 90 degrees. Now, at the same time, there's a stick. Okay? So along the same ground, there's going to be a stick. And the stick is 3 meters tall, and the stick is going to make a 4-meter shadow. That we're able to measure quite easily, and it's happening at the same time as our tree is making our shadow, okay? So what that means is that the sun is at the same place in the sky. Now our stick is going to be making 90 degrees. And when we look at these two triangles, it seems fairly obvious to us that we're looking at similar triangles, but we may need a little bit more convincing of that. Now, remember, the nearby tree, we're able to figure out 15 meters along the ground. So, once again, I want to set this up. We got a tree, we got a sun. The tree, we can measure 15 meters along the ground. We can measure this shadow pretty easily. We just walk it off and see what it is. We have a pole. Our pole is 3 meters tall. We put it on the ground and it makes a 4-meter shadow, and we can see how long that is and we can measure that. So everything's easily measurable from the ground. I didn't have to climb the tree or do anything special. What I'd like to show you is what happens if I pick this pole up and place it right here. What if I pick that pole up and place it right there? So that it's now 3 meters here, and we know that this distance here is 4 meters from here to here. Now we can pretty much see that this angle is the same in both of the triangles, right? It's the same in this big triangle, and it's the same angle in this little triangle. And we know that we get a 90 in both of these. And so if that angle plus 90 give me this angle, right? Because 180 minus 90 minus that, and I have 180 minus 90 minus that will give me this angle. That means that these two angles are equal, which means that this angle here is equal to that angle up here. So what I actually have here are two similar triangles, and I can prove that because the corresponding angles are equal. What I've got is I'm going to name this triangle, maybe we'll call it A, B, C, so that's the big triangle with just the tree, and then we'll call this one D, E, F. And when I pick this up and put it here, it's actually D, E, and C again. So it all depends how I want to draw this diagram, if whether or not I have a separate F or whether F actually becomes the same point as C. And it doesn't matter to me which one we deal with, but we need to pick one to work with. So I'm going to work with this one for now. I'm going to work with this big one. So what we notice is that we have two triangles. We have the tree triangle, and that triangle is ABC. And that triangle, we're going to look at it in comparison to the smaller triangle, triangle DEC, which is the stick triangle. So we got a tree triangle, and we got a stick triangle. We're going to notice that angle A equals angle D, and we talked about why that is. We're going to notice that angle B equals angle E. They're both 90. And we're going to say that angle C equals angle C. It's the same angle. So when I drew it this way, it's the same angle, but as we talked about before, it's the same angle here. So since that's true, that means something. Therefore, triangle ABC is similar to triangle DEC. So that's very, very important. Once I've proven that they're similar, and the reason why they're similar is angle, 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 similarity. Now some of you might be able to see that we don't really have to show all three angles. Showing any two will be enough, because let's go back to that for a second. If this is 90 and this is 90, and if they both share this angle, then through angle sum of a triangle theorem, the fact that they have to add up to 180 degrees means that this angle has to equal this angle. So it would be good enough just to show that two angles were correspondingly equal. We don't actually have to show all three, and if you just do two, then you're going to say angle, angle similarity. And if you do all three, then you'll do angle, angle, angle similarity. But because of this, we know that they're similar. Once we know that they're similar, we know something about the side length ratios. So the length of the tree, AB, divided by the length of the pole, 3, is going to equal A or BC. Now BC is the total length of the shadow, so that's going to be 15. And that's going to be EC, which is the shadow of the pole, which is 4. And then it's going to be AC, which is the length of the sun ray, and nobody cares about it. And DC, which is the length of the ray from here, and again, nobody cares about it. I don't need it to solve this question. I have what I need in just these two. So the length of the tree divided by the length of the pole equals the length of the shadow of the tree over the shadow of the pole. So to do this, what I'm going to do is I'm going to multiply both sides by 3, and I get 15 times 3 divided by 4. So that's going to be 15 times 3 divided by 4, and it's going to be 11.25 meters. That's going to be the height of the tree. And I didn't have to climb the tree, and I didn't have to cut the tree down. I was able to figure out its height by going out with a simple stick and measuring the lengths of the shadows. So there's example 1.